We have seen such images, not only the cartoon ones like these, but the real ones too. Landslides are a frightening reality that can strike without warning. But what causes these natural disasters to happen? And why do they seem to occur more often during the rainy seasons? To understand this, we must understand the concept of shear strength. In short, shear strength is the soil's ability to resist sliding along its internal layers. When the shear stress generated by some load or overlying materials exceeds this shear strength, failure occurs, leading to landslides. To understand this process better, let's look deeper into the interplay of hidden forces beneath our feet. Let's explore the concept of shear strength and Mohr-Coulomb theory. When a material, like soil, is loaded with external pressure, it develops an internal resistance to counteract the applied force. This internal resistance is called stress. Stress is defined as the force per unit area over which this force acts. These developed stresses inside the material are of primarily two types: normal stress and shear stress. Normal stress is the component or part of the stress that acts perpendicular to the cross-section of the material. This can cause material to either stretch, known as tensile stress, or compress, known as compressive stress. It is denoted by the Greek letter sigma and defined as the force per unit area, as this is also a stress. In soil engineering, we usually encounter only compressive type of normal stresses. We have seen earlier that this compressive stress can lead to settlement of the soil. On the other hand, shear stress occurs when a force is applied parallel to the cross-section of a material, causing it to deform or slide in a shearing motion. Shear means to cut or divide something into two parts, especially by sliding one part over the other. So when a material or soil experiences shear stress, the stress tries to move and slide part of the soil mass relative to the rest of the soil mass. It is denoted by the Greek letter tau and is also defined as force per unit area. Soils are rarely exposed to direct shear forces. Instead, shear stresses often arise indirectly when soil is subjected to compressive loads. When soil is compressed, the load is transferred from one particle to another. This transfer happens at the point of contact between the particles, which are often at angles. This angled load transfer can induce shear stresses along the planes where particles touch. Additionally, when soil is under load, it tends to settle more than its adjacent layers, causing a relative movement between them and resulting in shear stress development at the edges. Another factor is that when compressive loads are applied, the soil tends to expand sideways. This lateral expansion also creates shear stress within the soil structure. This shear stress tries to move part of the soil mass related to the rest by sliding. However, the soil material resists this motion. The maximum resistance that soil can provide against shear is known as the shear strength of the soil. When this resistance reaches its maximum value, cracks may appear in the soil and soil is said to have failed. In other words, shear strength is the capacity of the soil to resist shearing stresses just before failure occurs. But where does this shear strength in soil come from? Soil's shear strength comes from three main sources. First is friction between particles. Soil particles rub against each other, creating a resistance to sliding. This is particularly important in sandy soils where densely packed particles interlock and increase friction. Second source is cohesion and adhesion. Some soil particles, particularly clay particles, bind together, which is known as cohesion, and cling to other surfaces, which is known as adhesion. This helps soil resist shear stresses. Third source is interlocking of particles. When soil particles fit together like puzzle pieces, they create a strong structure that resists deformation. This interlocking is a major source of shear strength, especially in dense sandy soils. But unlike other civil engineering materials such as steel or concrete, the shear strength of soil is not a function only of the material. It also depends on the stresses applied to it and how those stresses are applied. Same soil can exhibit different shear strengths under different field and engineering conditions. When soil is under stress, it can fail and slide along any surface. This type of failure is known as a shear failure, and it is the most common way soil fails. So, it is important to look at the stress conditions at any given point within the soil to understand how and when it might fail. When a soil is subjected to loading, it experiences stress at every point, all the way down to the bottom. At each point within the soil mass, we can imagine countless planes passing through it, each with different magnitudes of stresses acting on them. Generally, both normal and shear stresses act on each of these planes. On one of these planes, if the shear stress becomes higher than the shear strength of the soil at that plane, the soil fails. This plane is called failure plane. We find something interesting here. There are three planes at right angle to each other where the shear stress is always zero. These planes are called principal planes, and the stresses on these planes are known as major, intermediate, and minor principal stresses. These stresses are denoted as sigma 1, sigma 2, and sigma 3. In soil studies, it is often convenient and usually sufficient to consider only two-dimensional analysis. This means we focus on major and minor principal stresses and can safely ignore the intermediate principal stress. Even though this introduces some error, this error is typically small enough to be negligible. At any point in the soil, let us consider a small soil element. If we know the stresses acting in two mutually perpendicular planes, we can determine the stresses on any plane that is at any angle from these two planes. Let's say the stresses acting on these planes are sigma x, sigma y, tau xy and tau yx. And we want to know the stresses on a plane that is at an angle of theta from the plane with the stress sigma x. The normal stress and shear stress on this new plane can be given as these equations. These equations can be obtained by simply balancing the forces on the plane of interest. One German scientist and civil engineer, Christian Mohr, realized these stresses at a point can be represented graphically. He then developed an extremely useful device known as Mohr Circle of stress. The Mohr Circle represents these equations in a manner that makes them more easily understood and remembered, and it brings out their physical significance more clearly. To draw a Mohr circle, we first rewrite the equations after a little rearrangement. Next, we square both the sides of the equations and add them together, This gives us a new equation. This equation represents a circle with the following form. The center of this circle can be given as this, and its radius is given by this. To draw the Mohr circle, we plot the normal stress along the x-axis and shear stress along the y-axis. We start with two given stress points. We mark sigma x and sigma y on the normal stress axis, assuming sigma x is greater than sigma y. Note that tau xy and tau yx are equal in magnitude but opposite in direction. We mark these points on the graph and connect these 2 points to form a diameter of the circle. The center of the circle is the midpoint of this diameter. We can also find the center by calculating the midpoint of the 2 normal stresses on the x-axis. With these points and the diameter, we can draw the Mohr circle. This circle always lies on the normal stress axis. Each point on the Mohr circle represents the normal stress and shear stress acting on a particular plane passing through that point in the material. The Mohr circle is an incredibly useful tool for engineers. It helps in determining various stresses and provides valuable insights. The principal stresses can be easily spotted and determined, and their orientation can be easily measured or calculated. These 2 points on the circle represent the major and minor principal stresses, sigma 1 and sigma 3, which are the maximum and the minimum normal stresses. We can see that these points satisfy the definition of principal stresses because the shear stresses at these points is 0. The center of the circle can also be written in terms of major and minor principal stresses as their midpoint. The radius of the circle in terms of principal stresses can be written as this. We created this Mohr circle by considering a general soil loading scenario where the soil experiences both horizontal and vertical stresses, including shear stresses. These stresses are not necessarily the maximum or the minimum that soil experiences. Therefore, to simplify the analysis and to create a scenario similar to what we create in the lab, we consider that the horizontal and the vertical stresses are the maximum and minimum stresses that a soil sample is experiencing. Hence, these sigma x and sigma y become sigma 1 and sigma 3 respectively. So these stresses become principal stresses, and the planes on which they act become principal planes. We know that on principal planes, shear stresses are 0. Using the equations, we can determine the center and the radius of the Mohr circle. The center of the Mohr circle is at this point and its radius is this. With these values, we can draw the Mohr circle. We should note that any plane in the soil mass that is at an angle theta from the principal axis will have its stresses on the Mohr circle at a point that forms an angle of 2 theta with the principal axis at the center of the circle. Also, we can see that the point located at the top of the Mohr circle represents the maximum shear stress acting on some plane within the soil. It is clear from the circle that this maximum shear stress is equal to the radius of the circle. As we move in either direction from this point along the circle, the shear stress values decreases. Therefore, the magnitude of the maximum shear stress that can occur on any plane in the soil is equal to the radius of the Mohr circle. We can see that the point representing the plane of maximum shear stress makes an angle of 90 degrees at the center of the circle with the point representing the principal stress. Hence, the plane makes an angle of 45 degrees in the soil mass. It might seem obvious that soil would fail along the plane where the maximum shear stress occurs. But surprisingly, that is not always the case. To estimate the angle and the plane of failure and the magnitude of stresses in the soil at the time of failure, several different theories have been proposed. One of these theories is Mohr's rupture theory. This theory is widely applicable and helps us understand the failure conditions in various types of soils. We notice that if more load is applied to the soil, more difficult will be to shear it, compared to shear a soil that supports smaller load or no load at all. Hence, we can see that shear strength depends on the normal stress of soil. As increased normal stress on soil increased the shear strength of the soil. According to Mohr, failure in soil is caused by a critical combination of normal and shear stresses acting on the plane of failure. To understand this, we gather data from several tests carried out on different soil samples up to the point of failure. We then plot a series of Mohr circles, each representing the data from one test. It is convenient to show only the upper half of the Mohr circle. We locate the points of failure for different samples on their respective Mohr circles. A line connecting these points and tangential to these Mohr circles can be drawn. This line is not a perfect straight line, and it is called the Mohr failure envelope. By observing this relationship, Mohr established that shear strength is a function of normal stress. Coulomb's earlier researches and Mohr's investigations found that it is safe to assume this curvy failure envelope as a straight line. This relationship between normal stress and shear stress can be expressed as a linear equation like this. Here, tau is the shear stress at failure, sigma is the normal stress, c is the cohesion between the particles, and phi is the angle of internal friction, which represents the frictional resistance between soil particles. Mohr-Coulomb's theory accounts for both cohesive strength and frictional strength of the soil. Now, if we look at the graph, we see that the straight line, the straight failure envelope, intercepts the vertical shear stress axis at a point. This intercept represents the cohesion C. Also, the slope of this line gives us the angle of internal friction phi, also known as the angle of shearing resistance. From the Mohr-Coulomb theory, we can infer two key things. The Mohr circle represents the state of stress in the soil at a point, while the Mohr envelope represents the shear strength of the soil. If the stress at a point in the soil mass creates a Mohr circle that is entirely below the Mohr envelope, the soil is safe and stable. This means the stress is within the limits and the soil can handle. However, if the soil is stressed further, maybe due to increased load or other factors, the Mohr circle grows larger. There may come a point when this circle just touches the Mohr envelope. At this critical moment, the stress developed in the soil has equaled the shear strength of the soil, indicating the stress in the soil has reached the point of maximum resistance on this plane. This is the point where cracks in the soil may start to appear, and we say that the soil has failed in shear. Once the soil has failed, it cannot be stressed further because it will not take any additional stress and will collapse. Therefore, any Mohr circle that crosses the Mohr envelope cannot exist, as it would imply that the soil has already failed. Using the Mohr circle, we can also determine the angle of the plane on which soil fails by shear. The angle is denoted by theta f and is measured from the major principal plane. It forms twice the angle at the center of the Mohr circle. This angle can be expressed in terms of the angle of shearing resistance phi. From the diagram, we can certainly write this and theta f can be written as this. Now this is interesting. Soil does not fail on the plane on which the shear stress is maximum, and that is at angle 45 degree from the principal plane. Failure angle theta f become equal to 45 degree only when phi is 0. That is when soil provides no internal resistance due to friction and the Mohr envelope is horizontal line. This will happen in the case of so-called purely cohesive soils. Phi is related to the internal friction that is predominant in the soils like gravel and sand. This is why these soils are sometimes referred to as phi soils or frictional soils. On the other hand, C is related to the cohesion between particles, which is a main characteristic of clay soils. That's why clay soils are also called cohesive soils. Between these two types of soils lie silt soils, which can display some amount of both internal friction and cohesion. While they are often characterized as C-phi soils, their behavior can be quite complex and varies depending on specific conditions. Later research show the parameters C and phi are not actually fundamental soil properties like it was initially thought. They can change based on things like water content, drainage, and how you test the soil. Also, Terzaghi figured out that it's the effective stresses, not the total stresses, that really control the soil's shear strength. So the equation was rewritten in terms of effective stresses as this, where C dash is the effective cohesion and phi dash is the effective angle of shearing resistance. This equation is also known as a revised Mohr-Coulomb's equation for the shear strength of the soil. This is one of the most important equations of the soil engineering. Mohr-Coulomb's theory aligns fairly well with both field and laboratory observations of soil failure, making it a useful tool for estimating soil shear strength. However, it's not without its limitations. The theory assumes a linear relationship between shear strength and normal stress and approximates the curved failure envelope by a straight line, which in reality may be non-linear for some soils. So it might not give correct results for some soils. Then it neglects the effect of the intermediate principal stress, which may lead to inaccuracies in predicting failure plane. Then the theory does not account for the stress history of the soil, which can significantly affect its strength and behavior. Also, the theory assumes that the soil is isotropic, meaning its properties are same in all the directions, while soils in the field are anisotropic, which can affect their strength and deformation characteristics. All types of slopes, be it hills, mountains, riverbanks, or even man-made cuts and fills, remain stable only if the shear strength of the material of which they are composed is adequate. Factors such as rainfall increases the pore water pressure in the soil, which reduces the shear strength of the soil. Also, it adds more weight to the soil. The combination of increased weight and reduced shear strength makes the soil more likely to slide, leading to landslides. I would like to thank my patron for supporting elementary engineering financially. Also, if you think elementary engineering has given you knowledge that's worth something to you, consider supporting this channel on Patreon and get access to the questions and their solutions related to various topics of soil mechanics. Your support will help me continue creating more such valuable content. If that doesn't resonate with you, spreading a word about elementary engineering will also be of great help. Only your love and support keeps elementary engineering going. You can find the links of books and other sources I referred for the creation of this video in the description. Read Shear Strength and Mohr-Coulomb Theory at elementaryengineeringlibrary.com. All the links are in the description. Thank you.